Optimus will be epic. That is what Elon Musk recently posted on X, showing his confidence in Tesla's humanoid robot. But before Tesla can produce millions of Optimus robots, it needs to answer one basic question. Can Optimus V3 consistently perform the tasks people actually need every day? That question became even more important after Ashoka Laswamy, Tesla's head of autopilot and AI, posted a short correction on X, correction, 10 million robots. The statement reflects Tesla's long-term production ambition, but it also creates a much bigger question. What useful work will 10 million humanoid robots actually perform every day? The answer is not dancing, running, or doing backflips. Those demonstrations can attract millions of views online, but they generate almost no real economic value. Tesla's entire investment thesis depends on something much less spectacular and much harder to accomplish: creating a humanoid robot that can cook breakfast, wash dishes, fold laundry, vacuum floors, clean bathrooms, organize groceries, carry heavy shopping bags, make beds, and assist elderly family members for hours with little or no supervision. If Optimus cannot perform these ordinary household jobs reliably, producing 1 million or even 10 million robots becomes almost meaningless, because there would be little practical reason for consumers to purchase them. This is also where Tesla's approach starts to differ from many of its competitors. Boston Dynamics Atlas continues to showcase extraordinary agility. Units G1 can run, jump, perform martial arts-style movements, and execute highly dynamic actions at a relatively affordable price. Figure AI has concentrated heavily on warehouse automation, while Agility Robotics Digit is already performing logistics-related tasks in controlled commercial environments. These are impressive engineering accomplishments, but none automatically proves that a humanoid robot can survive the unpredictable conditions inside a normal home. A family is not purchasing a humanoid robot because it can perform an impressive backflip. They want something that can wash dishes without breaking them, prepare food without spilling hot soup, fold clothes properly, carry groceries upstairs, or safely assist an elderly parent. Household work requires precision, adaptability, and reliability far beyond athletic performance. That is why Tesla appears to be focusing heavily on manipulation intelligence, rather than simply producing impressive demonstration videos. According to Tesla's current technical direction, Optimus V3 is expected to have 22 degrees of freedom in each hand, roughly twice the previous generation's 11 degrees of freedom, along with nearly 3 times as many tactile and force sensors. These upgrades are not primarily intended to make Optimus appear more human. They are meant to make the robot function more like a human. Walking through a kitchen is relatively simple compared with picking up a wet ceramic plate, cracking an egg without crushing it, pouring hot coffee into a cup without spilling, loading a dishwasher filled with objects of different shapes, or folding clothing made from different materials. Every one of these actions requires continuous changes in grip strength, finger placement, wrist position, and applied force, sometimes dozens of times in a single second. Tesla's redesigned tendon-driven hand architecture reflects exactly this goal. Instead of placing large actuators directly inside the fingers, Tesla moves most of the motors into the forearm and transfers their force through bio-inspired tendons similar to those found in the human body. The result is a lighter hand with reduced inertia, quicker response, improved precision, and more room for tactile sensing equipment. Elon Musk has repeatedly described the Optimus hand as one of the most difficult and expensive engineering challenges, because it has to satisfy 2 seemingly opposite requirements simultaneously. It needs enough torque to lift objects weighing more than 18 kilograms, while also being gentle enough to handle an egg, a drinking glass, a battery cell, or fragile kitchenware without damaging them. Solving this balance is much more valuable than teaching a robot another athletic trick, because successful household automation depends primarily on dexterity rather than speed. The intelligence controlling those hands is equally important. Optimus V3 is widely expected to use Tesla's next-generation AI5 computing platform, replacing the AI-4 hardware currently used in Tesla's production vehicles. But a household creates a much more complicated artificial intelligence challenge than a road. A self-driving vehicle mainly needs to predict the behavior of cars, pedestrians, cyclists, traffic signals, and other road users. A household robot must recognize thousands of everyday objects, determine whether a cup is empty or full, estimate the weight of a grocery bag, identify whether a cooking pan is hot, avoid children's toys, detect unpredictable pets, and immediately modify its movements as the environment changes. Every household task combines computer vision, force sensing, balance, motion planning, and physical reasoning at the same time. That is why many robotics researchers consider physical AI considerably more difficult than autonomous driving. Ultimately, none of these hardware improvements matter unless they contribute to Tesla's larger economic objective, bringing the cost of useful physical labor down toward roughly $1 per hour. Elon Musk has repeatedly argued that Optimus is not simply another consumer robot. Instead, he sees it as a platform that could fundamentally change the economics of labor. As production eventually approaches around 1 million robots per year, Musk has suggested that manufacturing costs could eventually fall toward $20,000 to $25,000 per unit, with a long-term selling price of around $30,000. Those numbers are significant not simply because they describe the cost of a robot. They describe the potential cost of labor. If Optimus can spend hours every day cooking meals, washing dishes, folding clothes, cleaning floors, carrying groceries, organizing homes, and helping elderly people with minimal supervision, then households are not merely purchasing a machine. They are purchasing thousands of hours of productive work. Every improvement in the 22 degree of freedom hands, tactile sensing, onboard computing, and manipulation software ultimately serves one objective: reducing mistakes until physical labor becomes affordable enough to compete economically with human labor. Tesla's learning strategy is built around this exact goal. The first Optimus robots are expected to remain inside Tesla factories before eventually entering consumer homes, because factories offer a more controlled environment for gathering enormous amounts of real-world training data. Every completed task, every unsuccessful attempt, and every correction can provide additional information for the AI system. As Optimus observes workers, repeats tasks, recognizes mistakes, and improves through software updates, knowledge gained by one robot could eventually benefit the entire fleet. Elon Musk has also suggested that future Optimus systems could speed up learning by interpreting instructional videos and demonstrations, allowing robots to acquire practical skills much faster than traditional robots that require engineers to manually program every movement. Over time, millions of robots sharing their experiences through software updates could potentially improve at a pace that isolated humanoid robots would struggle to achieve. In the end, Optimus V3 does not need to prove that it is the fastest humanoid robot or the most impressive performer on a stage. It needs to prove something much harder: that it can become a dependable household worker people can trust every day. If it can prepare meals, clean kitchens, fold laundry, organize groceries, vacuum floors, assist elderly family members, and repeat those tasks safely and consistently, Tesla's ambition of producing 10 million robots annually starts to look commercially realistic. If it cannot, then even the most advanced AI chip, the most sophisticated robotic hand, or the world's largest manufacturing facility will not be enough. The real success of Optimus V3 will ultimately come down to one simple question: can it perform everyday household labor well enough that millions of families would actually want one inside their homes? But there is another major question. How can Tesla make millions of robots smarter by allowing them to learn from one another? Is Tesla's fleet learning approach truly a technological breakthrough, or is it a theoretical concept with serious weaknesses? The idea sounds extremely powerful. Imagine a robot at the Fremont factory learning how to correctly grasp a component, and then instantly sending that knowledge through the network via over-the-air updates, allowing millions of other robots around the world to reproduce the same behavior. It sounds compelling, but does this idea collide with the harsh physical limitations of the real world? One of the biggest technical challenges comes from mechanical differences between individual robots. Even when thousands of units are produced on the same assembly line, no two machines will be perfectly identical. One joint could be slightly looser by 0.1 millimeters. One motor could operate 2 degrees Celsius hotter. One force sensor might be 5% more sensitive than another. So can a neural network optimized for robot A's exact mechanical characteristics operate perfectly on robot B without causing it to drop or break a glass? When a robot performs extremely precise manipulation, requiring millisecond-level accuracy, tiny mechanical differences can cause a shared AI model to fail unless the system continuously recalibrates each individual machine. This raises another question. Is Tesla extending the success of its autonomous driving data strategy too far when applying the same concept to humanoid robots? Elon Musk frequently points to Tesla's enormous database containing billions of miles of driving data. But how much of that information actually helps a machine learn how to fold laundry or wash dishes? Autonomous driving data mainly addresses visual perception and vehicle control involving variables such as steering angle, acceleration, braking, and road positioning. The central challenge for Optimus's 22 degree of freedom hands is very different. It involves tactile sensing, friction, material interaction, and precise physical manipulation. Billions of miles of road footage might help Optimus understand its surroundings and avoid obstacles, but that data does not teach the robot how to hold a spoon correctly or tighten a bolt without damaging the threads. The manipulation dataset for Optimus must largely be collected from the ground up, which significantly limits how much Tesla's existing FSD data can directly transfer to humanoid robotics. There is also another major issue: data storage. Who pays for the enormous storage and processing infrastructure required as the robot fleet grows? An Optimus unit operating 8 to 10 high-resolution cameras alongside hundreds of force sensors running at high frequency could generate enormous quantities of information every day. If Tesla deploys 100,000 robots, the amount of incoming data could potentially reach hundreds of petabytes per day. The bandwidth requirements, cloud infrastructure, and storage expenses associated with such a system could become enormous. Tesla would therefore need to process and filter much of the information directly at the edge. But that creates another critical challenge. How does an edge computing system determine which information contains valuable training data and which information is simply redundant noise? If the filtering system makes the wrong decision, Tesla's central fleet learning model could end up training on low quality or irrelevant information. Despite these major challenges, why is Tesla placing so much of its physical AI strategy around fleet learning? The answer is simple: Tesla may not have another realistic path toward the scale it wants. Traditional programming using fixed rules has struggled against the enormous complexity of real-world environments. Meanwhile, competitors such as Figure AI and Boston Dynamics have relied heavily on teleoperation, including VR-based systems, to collect training data manually. But this can produce only limited amounts of data compared with what would be required to train millions of capable household robots. Tesla is instead accepting the trade-off of turning facilities such as Fremont and Gigafactory Texas into real-world testing grounds, where thousands of robots can perform tasks, make mistakes, and interact with physical environments while collecting valuable training information. The fleet learning approach still faces serious technical bottlenecks, but it could represent one of the few practical ways to move humanoid robots from experimental prototypes toward large-scale commercial deployment. If Tesla succeeds, Optimus could become much more than a factory worker. It could fundamentally change how millions of people live and work every day. Do you think Tesla's Optimus V3 is finally getting close to handling everyday household tasks? Or does the robot still have a long way to go? Let us know your thoughts in the comments below. Thanks for watching. Make sure to hit the like button, subscribe to the channel, and turn on notifications so you don't miss our next breakdown. See you in the next video.